Welcome to the Odyssey of the Atom, the journey of U-465. This chunk of raw uranium ore, dormant for 2 billion years, holds enough potential energy to power 400 homes for a year. But to release this power, this rock must undergo an extreme transformation. This is the paradox of potential. While U-465 is a rich deposit, raw uranium cannot sustain a reaction and cannot even power a single light bulb. The useful isotope, U-235, is locked inside useless U-238. Solving this requires building some of the most secretive facilities on the planet. The first step is the ice fortress. U-465 is in water-saturated sandstone, making mining difficult. We employ a freeze plant that pumps -30°C brine through pipes, creating a frozen wall of ice. This holds back millions of gallons of groundwater until the ground is a solid block of ice. Next is the remote harvest. The radiation is lethal to humans, so operators work from sealed booths 50 meters away, using a remote tram to scoop up the ore. Drill bits studded with tungsten carbide chew through the frozen rock before the U-465 is pulverized and mixed into a radioactive slurry. The chemical key is separating the uranium from the waste rock. The slurry is delivered to the mill, where special acid dissolves only the uranium. The output is a yellowcake solution, a compound that is essentially U-3O8. Precise temperature control is critical here. U-465, now black powder, is sealed in a drum and begins a 2,000-kilometer journey. This is the Rolling Vault, a truck with reinforced steel walls, GPS tracked by the IAEA. The route is classified, and armed guards watch while drivers sleep. At the conversion plant, the solid powder must become a gas to separate the isotopes. At 550°C, the powder meets fluorine gas, one of Earth's most reactive elements. The result is uranium hexafluoride, or UF6, a gas so corrosive it can dissolve bones. We face the isotope challenge. U-238 is 99.3% of the mass, and U-235 is only 0.7%. They are chemically identical. The only difference is U-235 weighs 3 neutrons less. We use physics, centrifugal force, to exploit that tiny weight difference for enrichment. The gaseous UF6 enters a cascade of centrifuges. Spinning at 60,000 RPM, the heavier U-238 is pushed to the wall, while the lighter U-235 hovers in the center. Through thousands of these machines, the U-235 concentration is gradually pushed from 0.7% to the reactor-grade target of 3 to 5%. The enriched gas is converted back into a solid ceramic powder and pressed into pellets. A single pellet contains as much energy as 1 ton of coal. Every pellet must be microscopically inspected for hairline cracks. A single defective pellet could cause a reactor shutdown. These pellets are stacked into zirconium alloy tubes, engineered to withstand immense pressures. These tubes are bundled into precise patterns, over 200 tubes per bundle. The finished assemblies are sealed in armored containers, ready for transport. The journey ends at the reactor vessel, a 40-foot-tall steel structure, the Cathedral of Steel. Robotic arms, guided by operators in radiation suits, insert the assembly. The geometry must be perfect for safety, and as the control rods withdraw, the neutron levels begin to climb. Ignition. The first U-235 atom splits. The chain reaction begins, turning water to steam and spinning turbines. The worthless rock is now priceless energy, powering hospitals, warming homes, and keeping the ancient promise of the atom.